So welcome to Robotics 2. In today's lesson, we are going to look at the low fidelity simulation of the quadcopter. Now, before we start, here is where we stopped in last class. So we have the quadcopter equation of motion. So quad equations of motion. So, and I'm going to write this equation because it needs a short discussion. So first equation is x1 dot is equal to x2. Second equation is x2 dot is equal to 0, 0, g plus 1 divided by m. Then you have the rotation matrix, thrust in the body coordinate frame plus 1 divided by m drag force fd. Then we have the equation x3 dot is equal to 1, 0 minus sine theta 0 cosine phi cosine theta sine phi 0 minus sine phi cosine theta cosine phi. And this is inverted, multiplied by x4 dot is equal to torque in phi direction multiplied by Iyy torque in theta direction. Sorry, this first is Ixx, second one is Iyy, third one is torque and Izz. And what you have is basically this is inverted, this is inverted, this is inverted, minus you have Iyy minus Izz, Ixx, omega x, omega y, omega x, omega z, then Izz minus Ixx divided by Iyy, omega x, omega z, and last but not least, it's Ixx minus Iyy divided by Izz, omega x, omega y. Believe it or not, these are the same, these are the 12 equations. As you can see that there are 3 equations here, 3 equations here, 3 equations here, and 3 equations here. So you have these 12 equations that describe the 3-dimensional dynamics of the quadcopter. However, what I want to do is I want you to carefully look at this equation. Now, this equation is written in the inertial frame. Remember inertial frame? So basically you have this flat earth and then you have northeast down and then we have this quadcopter. So, and the quadcopter has its own frame, which is north, east, down. This frame is inertial frame, and this frame is the body or aircraft body fixed frame. So Earth center, Earth fixed, Earth center coordinate frame, and this is aircraft body coordinate frame. This equation is written in aircraft body coordinate frame. Now, some of you may ask me, how is this possible? So please understand, any vector in body coordinate frame, any vector in ABCF can be transferred to inertial frame using the rotation transformation of roll, pitch, and yaw. So basically, this thrust in the body frame, this is in the body frame, is transferred using this rotational coordinate frame, and this gives you thrust in inertial frame. This FD is the drag, and this drag is found out in the inertial frame. So the second set of equations are in inertial frame, and last three equations are in the aircraft body coordinate frame. Everyone understood this? This is an important distinction. So you can see the equations, they can be written in inertial frame or they can be written in the body frame, but you have to use the appropriate transformation matrix that will take you from body frame, aircraft body frame, to Earth centered coordinate frame. Now, at this point, what I want to do is, before even we start doing anything with the controller, I just want to go through the Matlab simulation and explain the code line by line. And once we are done with that code, we can actually discuss how the controller is designed. So at this point, I'm gonna share my screen. And what I would do is I would explain these equations, how they are coded inside the Matlab. Any questions before I share my Matlab screen? So can you see my Matlab screen?
Yeah, we can see it.
Yes.
Fantastic. So now what I want to do is, you should be looking at simulate. So this is a simple simulation of a quadcopter, and this simulation is using something called as the Euler integration. What do I mean by Euler integration? Euler integration is acceleration multiplied by time gives you velocity. Velocity multiplied by time gives you displacement. So first is simulate, and it can do multiple ways. It can take a controller, it can run without a controller. So first we are going to run it without the controller, and later we are going to run it with the controller. So there is data, which is the output of the simulation. That actually is the x values. Those are the distances or the displacements in the inertial coordinate frame. Values of theta, which are the angular orientations. Velocity, which is the derivative of x. And then you have the angular velocity. And those, again, they are used in these equations. So line number 21 to 26 is giving the values of gravity, mass, length, which is the length from the motor to the center of the quad, value of K, value of B. So those are the constants that are used in simulation. So if we don't supply any argument, that's what it's saying. Nargin means if you don't supply argument, or if your arguments are less than 4. See, there is controller, there is t start, t end, and dt. So this function simulate needs 4 arguments. For some reason, if you supply any less than 4 arguments, then what it's going to do is it's going to just run the simulation without the control. And that's why if there is no argument, then it will actually run the simulation from t is equal to 0 to 2 is equal to 4, because for simulation to run, it's going to need a start time, which is 0, end time, which is 4, and time step, which is 0.005. Next is basically this talks about the number of points in simulation. So it creates a number, and that is how many times the Euler integration loop needs to be calculated, or you need to run the Euler integration. 41 is just saving the space. It's creating an empty array. So you have x out, x dot out, theta dot out, and the input, which is the controller. So that actually is 0. Next is it's creating a structure. So for a moment, just ignore this controller parameters. We will talk about this when we go to the controller, but it's actually creating a controller structure. The next is from 51 to 53 is creating the x values, x dot values, and theta values. So basically these are the velocities and displacements. Next thing is if we don't have any controller, which means if you supply no argument, clearly that means there is no controller. It's just saying that the values of theta dot are 0. So we just want to see the stability of the quad. And what we want to do is we want to provide some sort of disturbance to the initial angular velocity. Initial angular velocity is 0. So we want to provide some disturbance to the initial angular velocity and then see how good or how bad the quad works. And clearly you can think about it. If there is no controller, if you add or if you disturb the quad, which is flat, so roll is 0, pitch is 0, yaw is 0, and the roll rate is 0, pitch rate is 0, yaw rate is 0, then if you have some disturbance, after some time that quad is inherently unstable, so it's going to become unstable. Next thing is you are initializing the index, and the reason this index is initialized to get the controller values. So we will talk about this a little bit later when we talk about controller. Next part is at every time step, the index is incremented. So when time is equal to 0, the index IND is 1, time is equal to 0.005. So step 1, index is going to be 2, and so on and so forth. Now, what that means is at every time step, if there are no arguments, then it's going to take some 0 input and then going to go forward. But if you specify certain controller, like a proportional controller or the derivative controller or proportional derivative integral controller, then it will invoke this function, controller function, and compute the controller values. The next part is I want you to see that there are these 3 important functions: theta dot to omega. Theta dot to omega will take theta dot and theta and find out the values of omega. Now, a word of caution. Theta dot is different than omegas. Omegas are the values in body coordinate frame, aircraft body coordinate frame. theta dots are the values.
It's electrical.
Then you have this acceleration that is going to take the values at every time step, theta x dot m g k k d, and then you have omega dot, which is actually found out from the angular acceleration function. And these equations are actually implementing 3 out of 4 equations that I just wrote on the first slide. So next step, this is called as the Euler integration. Omega is equal to omega plus delta t multiplied by omega dot. Omega is the angular value, the angle value, which is the previous angle value, plus delta t time step multiplied by the velocity. So angular displacement, the new angular displacement is the original angular displacement, which is omega, plus delta t multiplied by the velocity. Here we are actually using this conversion, that code we already looked at earlier, and then we are advancing theta, then we are advancing x dot, and then we are advancing x. So you can think about it like this is the integration in its basic form, which is time step multiplied by the slope plus the previous value. And then these values are actually stored in the structure. And if you go down, let's look at step by step. So this is just an arbitrary input. If there is no controller, you are checking the input value. And then this is the input. Then these are the values of the thrust from the basis of input. So 0, 0, there is no thrust in z direction. There is no thrust in y direction. And there is no thrust in x direction. There is no thrust in y direction. There is thrust in the z direction. So based on the input, you have these thrust. So think about inputs are like the speeds or the square of the speeds of the motors. Next thing, we have to find out the torques. And if you look at the thrust is in the body frame, that is absolutely correct. And then we multiply that by rotation matrix to get the thrust value in the inertial frame. So that's coming next. So torques is the L value, which is the lever arm, multiplied by K, multiplied by the difference between omega 1 square and omega 3 square, then omega 2 square, omega 4 square. So these are the torques about roll, pitch, and this the last one is torque about yaw. So these are the values of the torques. The next part is the function acceleration. Please note A, and this is where, and I want you to look at this equation very, very carefully. This is the second set of equations. X2 dot is equal to 0, 0 g plus 1 over m r times t plus 1 over m fd. So please understand, these are the equations, the second set of equations that I just wrote on the first slide. And I want you to take a minute just to make sure that these equations they make sense. So please look at these equations. This G should be positive. Moving on, then you have these angular accelerations. So these are the last set of equations, which are last 3 equations. You have omega GAD, angular accelerations input, omega ILBK, Then you find out the torques, and then omega d, which is x4 dot, is equal to inverse of I multiplied by all the taus minus cross of omega I omega. So this is actually I use a Matlab built-in command which is called cross for finding out cross product, but you can actually go to actually you can find out omega d. So last function is omega, wherein you are actually finding out the roll pitch yaws, p phi theta psi roll pitch yaw, and then finally what you have is you have this matrix that actually gives you the rotation. So this equation is the third set of equations. Omega is equal to w theta dot. So theta dot, and you have omega dot. Thetas are in body frame, omegas are in inertial frame. Okay, before I run the code, any questions related to the code? Can you see that the 12 equations that we just talked about, they are implemented here. Now we want to simulate. So what you do is you go say visualize, simulate. Okay, so you can change the path. So visualize test, simulate. So I'm gonna just add this to the path, change folder. And then we are gonna see. So please note, at this point, the simulation is paused. So you have to enter any key, just press any key so that the simulation can run. And I'm going to change my screen. So just so that you can see the simulation running. So are you able to get this simulation working? Yes, no? Okay. So fantastic. So with this, we are ready to go for the control. So next part of this discussion is how do we control? Now, so let's understand what do I mean by control. We have torques in roll, torques in pitch, torques in yaw. These are the things that we have control over. So we can change these. Now, how can we change those? The only way that can be implemented, this change can be implemented in hardware, is changing the speed of the first motor, changing the speed of the second motor, changing the speed of the third motor, and changing the speed of the fourth motor. So by changing the speeds of motor 1, motor 2, motor 3, and motor 4, you can achieve the different values of torques. Now let's start with something called as the equilibrium point. So equilibrium point. So initially, I'm going to assume that all my thetas are zeros. So theta, psi, phi, all these values are initially zero. I'm also going to assume the angular rates theta is equal to 0, phi dot is equal to 0, psi dot is equal to 0. So this is what I'm going to assume. So the torques are actually defined. Torques are defined as I multiplied by thetas. So basically, T is equal to I alpha. So if I use this, this is the value of torque. This is the moment of inertia. And this is the angular acceleration. So I'm going to assume my values of torques are proportional to I multiplied by a control input. So what does that mean? Is I'm arbitrarily going to say that my torque in the roll direction, torque in the theta direction, torque in the psi direction is going to be minus Ixx multiplied by Kd multiplied by the error rate plus Kp multiplied by 0 to t, the angular velocity integration. And I will explain in just a bit what I mean by that. Kd theta dot plus Kp 0 to t theta dot dt and minus Izz Kd psi dot plus Kp integration 0 to t psi dot dt. Now this equation, I will explain it to you in just a second. So this equation is, I'm choosing this equation at this point like arbitrary equation. So, and what is the physical interpretation of this equation? So I want to start with a very simple example. Say you are here and you are walking towards robotics 2 class. Okay, this is say person X. Person X sees person Y, maybe this is your friend. He is also walking towards robotics class. So Pikachu 150, say we are going to Pikachu 150. Person X is walking towards Pikachu 150. Person Y is walking towards Pikachu 150. Now you or this person X wants to ask this person Y, hey, are you done with homework? Are you done with homework? But clearly X and Y, they are quite far. So X needs to catch up with Y. So what would happen? X would speed up. So X would start walking fast with the hope that before person Y reaches Pikachu 150, X would be very close to Y, and then that person will be able to talk to him. So speeding up, this actually is the control. This is control. So let me give you some simple examples. If person Y is walking quickly or his speed increases, for X to catch up with person Y, he needs to speed up. If person Y stops, then X could potentially continue with the same speed or reduce the speed to catch up with y. But if person y slows down, then person x can potentially slow down and still catch up to person y based on the relative speeds, so that they can talk to each other before they reach Picacho 150. So what that means is the input to the controller. So whether the person x should speed up or speed down depends upon the relative distance between these two. So this is the relative distance between these two. So this is the basic proportional controller. So proportional controller means that when person x sees that person y is too far away from me, he's gonna speed up and he's gonna try to catch up to person x. So speed proportional to d. This is also called as the error because the distance between person y, so I'm gonna call this dy minus dx, is nothing but the error. So speed is proportional to error. This is proportional control. Everyone understood the physical interpretation of proportional control? Now, what happens? What is the issue with proportional control? So which means the speed is high if the distance is large, speed is low if the distance is less. There is no actual way you can try to visualize this. If what's going to happen is, as this distance is going to reduce, proportionately the speed is going to get reduced. What that means is, if you think about it, person x will always be some distance apart. He will not be at the location where y is. Person x, if person y is over here, person x would be at some distance away from person y. So how would we do that? How would we make sure that person x reaches exactly where the person y is? Or we don't want person x to overshoot. So for an example, if the value of d is changing because the person x sped up very quickly or sped down very quickly, then he could overshoot. Rather than reaching over here, he may go forward, backward, but not exactly at that point. So how would I take care of either the steady state error, or how would I take care of this overshoot? And that is where these additional components come in the picture. So what I'm going to do is, I'm going to control the speed, not only that is proportional to the distance between those two, but also the rate at which the distance is changing, d by dt of relative distance. And once I add this additional term, that becomes the derivative control. So this is proportional, then you have the derivative. But if you have the proportional and derivative control, unfortunately, you are gonna left with some steady state error. So for that, what you want to do is, you want to add the integration of distance. So integration of distance, and that becomes the integral term. So you have proportional, derivative, and integral term in PID control. That's why it's called P for proportional, I for integral, D for derivative, so PID control. Now, here is the basic problem with the integral term. There is a concept which is called integral windup. Integral windup. And I want you to think about this in your mind. So think about, if the distance is too far, the integral term we are integrating that too far distance, which means the controller effort that is coming from the integral term is more than what is ideally required. I will repeat this once again. If the disturbance is quite high, which means the error is quite high, or you are too far from your set point, so or you are too far from the person that you want to catch up to, if you use your integral term, that controller effort will be amplified, and that is not desired because that would create an overshoot or perhaps make the system unstable. So that is what is called as integral windup. So not a good idea to use an integral term when the disturbance is quite high, which means you are too far from your friend. So what they do is typically the integral term is turned off if the disturbance is quite high. What means if you are way too far from your friend, then you will not speed up or speed down based on the integral of the error or integral of the distance or distance multiplied by time. But once you get to a very close proximity, say for example, somewhere here in this region, then you turn on the integral controller to get to where that person is. And believe it or not, we humans do this unknowingly. So we speed up or speed down depending upon where the location is, depending upon what the errors are, and we implement the proportional integral derivative control unconsciously. But now we are giving some mathematical terms that would make this understanding clear. So let's look at the quad. We are going to assume that this quad has just one single 3-axis gyroscope. So with this gyroscope, I can only know theta dot, phi dot, and psi dot. There is just one 3-axis gyroscope. So gyroscope is giving me angular velocity, which is the derivative of angle. So this is giving me angular velocity. So that's why my derivative term directly is controlled by the angular velocities, theta dot, phi dot, and psi dot. So torque in roll direction is derivative multiplied by roll rate. Torque in theta direction is the derivative multiplied by kd, which is the pitch rate, and torque in psi direction, which is about the yaw, is yaw rate. So this is the derivative term in the control. Now, if I were to integrate psi dot, theta dot, and phi dot, what I would get? I would get phi, theta, and psi. So these guys, this is nothing but the angles. And that's why I'm having Kp. So the proportional is multiplying the angles. So everyone understood the physical interpretation of PID control. And in this quadcopter example, and some of our students just asked why minus. The reason for minus is initially the aircraft is at 0 pitch, 0 roll, and 0 yaw. If there is a disturbance that is causing the aircraft to roll up, pitch up, roll down, I want to apply the torque which is opposite of disturbance. So this negative sign is because I want to stabilize. So this has to be opposite of disturbance. So if the disturbance is positive theta, I want to apply the negative torque that would minimize that positive theta. However, if the disturbance is causing negative roll, I want to make positive torque so that that negative roll is compensated. That's why I have this negative sign. But the most important part is looking at the mathematical equations and then trying to give them some physical interpretation that makes understanding roll, pitch, yaw, and controlling roll rate, pitch rate, yaw rate with PID control more intuitive. Any questions before we go further on PID control? So essentially, we want the torque, all the torque to be on that at 0, because we just have control over torque. The next part is, this is great, but how would we physically implement? Please understand, quick recap. The only thing that is physical to our quadcopter are the rotor speeds. This is only the physical quantity. Everything else is derived or you get from these variations in omegas. So what I'm going to do is, I'm going to write the equation for torques. The torque equation is Lk. Remember, omega 1 square minus omega 3 square. Lk omega 2 square minus omega 4 square. And last but not least is omega 1 square minus omega 2 square plus omega 3 square minus omega 4 square. And this is going to give us torque in roll direction, torque in pitch direction, and torque in yaw direction. So these are the equations that we derived. Now we need to equate those to this hypothetical controller equations that we just derived. So KD 5 dot KP integral 0 to T P dot T dt minus IYY KD theta dot plus KP 0 to T theta dot dt minus IZZ KD psi dot plus KP integral 0 to T psi dot dt. Everyone understood? So this is the hypothetical controller that we are talking about. This is the controller equation. So this is the PD control. And this is the real thing. So real hardware. Now what we want to do is, we want to relate this real thing to this control law that we have provided. So this is sort of the algorithm. But here is the problem. The problem is, our real thing has 4 inputs: omega 1, omega 2, omega 3, and omega 4. But if you look at the proportional control or the logic that we have used, only has 3 equations. So there are 3 equations, but there are 4 unknowns. 3 equations, 4 unknowns. What are the unknowns? Unknowns are omega 1, omega 2, omega 3, and omega 4. But the relationship, there is only 3 equations. So we can't solve this. So for that, I'm going to use one more equation to help us. Thrust is equal to weight. So this is the simple equation. Thrust is equal to weight. Now the problem is, this equation is fine when the quad is in level flight, which means theta is equal to 0, phi is equal to 0. What happens if theta is non-zero and phi is non-zero? So what's going to happen is, just to give you an example, the quad would be something like this. And the actual thrust is going to be in this direction, but we want thrust in the vertical direction. So essentially, this equation goes down to mg divided by cosine of theta cosine of phi is equal to thrust. So what you have is you have the weight that is going in the downward direction, but you need to take the component of the weight and equate that to thrust. So now we have four equations, three equations here, one equation here, and that should give me the values of omega 1, omega 2, omega 3, and omega 4. Now, just for simplicity, I'm going to call omega 1 square is equal to gamma 1, omega 2 square is equal to gamma 2, omega 3 square is equal to gamma 3, omega 4 square is equal to gamma 4, just for simplicity. So what I need to do is ignore this left part. So I want you to look at this equation. I want to find out the value for gamma 1, gamma 2, gamma 3, and gamma 4. Value for gamma 1, gamma 2, gamma 3, gamma 4 from these four linear equations. And MATLAB would do that for you. You don't have to write it, but please understand these are simple algebraic equations. So there is some mathematical manipulation required, but you can find out these answers. And I'm going to just give you the answer. So to give you the answers, I'm going to define E phi, E psi, E theta. It just makes the life easy. E5, E psi, and E theta is nothing but the error terms, which is over here. So this guy is, it's better to write it over here. I'm going to call this guy E psi, E phi. I'm going to call this guy E theta. It just makes determination or finding the equations easy. And I'm going to call this E psi. Everyone understood? So basically this equation is, so it might be instructive just for to write the equation, so you realize that these equations become very simple. So L K gamma 1 minus gamma 3 is equal to minus Ixx E phi. Lk gamma 2 minus gamma 4 is equal to minus Iyy E theta. L, and then last equation is B gamma 1 minus gamma 2 plus gamma 3 minus gamma 4 is equal to minus Izz E psi. And last equation, which is gamma 1 plus gamma 2 plus gamma 3 plus gamma 4 is equal to mg divided by, in the case of quadcopters, this cosine theta cosine psi. Now you have 1, 2, 3, and 4. And what I want is gamma 1 is equal to something, gamma 2 is equal to something, gamma 3 is equal to something, gamma 4 is equal to something. Everyone understood this? What's happening? And you can use MATLAB to find these values, and I would just give you the equation mg 4k cosine theta cosine phi minus 2b e phi Ixx plus, and unfortunately these equations, even though this process is straightforward, the finding equation becomes complex. So let's use Matlab 2bkl for second, mg 4k cosine theta cosine phi plus e IGC 4b minus e theta Iyy divided by 2kl mg 4k cosine theta cosine phi minus 2d e phi Ixx plus e psi IGC k times L divided by 4bkl and mg 4k cosine theta cosine psi plus e psi IGZ divided by 4b plus e theta Iyy 2kl. So these are the equations or the results that you get when you try to find out gamma 1, gamma 2, gamma 3, gamma 4. And please note what are gamma 1, gamma 2, gamma 3, and gamma 4 is nothing but omega 1 square, omega 2 square, omega 3 square, and omega 4 square. Are you with me so far? Any question, concerns? Now, what happens now? The idea is, please understand, our algorithm, we need to have some value of Kp, we need to have some value of Kd. And from these Kps and Kds, once we will find from these Kps and Kds and the errors, basically error in roll, error in pitch, error in yaw, we are going to get the values of torques. From those values of torques, we are going to get gamma 1, gamma 2, gamma 3, gamma 4. That gives me omega 1, omega 2, omega 3, omega 4. And I would actually change in hardware using some PWM or some type of command those values, and that would stabilize and my hope is that would stabilize the pod. But please understand, it all depends upon how good my Kp and Kds are. So how good these values are. And it again, there are a lot of techniques to find out Kp and Kd. The best or the first approach is sort of trial and error, and then get the right values of Kp and Kd, and then see if it works. Then there are some rigorous mathematical technique wherein you do some optimization, some type of, and again, those tools are implemented in Matlab, and we'll look at those, not now, but step by step, and then try to stabilize the control or try to stabilize the quad. So the final hope is that once we use appropriate Kp and Kd, we go through this process, our quad will be stabilized. And that's just hope at this point. At this point, we don't know if it will really work or what would be the range in which it would work, or whether it would work for all the parameters, whether it would work when the quad is loaded, unloaded. But the hope is that we start with some Kp, Kd, run some simulations. Yes, so you can have a Kp for roll, Kp for yaw, Kp for pitch. You can have Kd for roll, Kd for yaw, Kd for pitch. They could be the same or they could be different. Or you can change Kps and Kds depending upon the runtime conditions. So you can do, those can be iteratively changed. So at first go, I'm going to assume all KPs and KD values are same for all angles. So KP for roll, KP for pitch, KP for yaw is same. KD for roll, KD for pitch, KD for yaw is same. All right. So now, since we got this equation, before I start, or before I do some type of simulation or run, I just want to make sure that everyone understood the physical interpretation of PID, and then we are going to implement in the code. Everyone understood? Any questions here before I go to the Matlab code? At this point, any question? If you have any questions, either you can unmute yourself and ask me questions, or you can use the chat window. I'm looking at the chat window to see if there are any questions. Okay, so now I'm gonna share my Matlab script. So here, now let's look at the control. So if you look at this control, step one is the type of controller. It could be the proportional control, it could be the PID control, or it could be just PD control. So if we don't supply any argument for controller, so if no argument, just is equal to 1, it means if the argument is number of arguments is equal to 1, then it will just go basic PID control, and it will use the basic values KD is equal to 4, KP is equal to 3, and KI is equal to 5.5. Are these the correct values? No, they could be different for different quads. So next thing, it's gonna see if it is a proportional control, you have this function that's actually going to find out the states for the proportional derivative control. If you have a PID control, then it's gonna find out the states for proportional, integral, and derivative control. So how does this work? So please see, for PD control, it will take the value of the state and it will find out the controller values. And the controller values, this is the basic equation for controller values. So first it's going to find out the state, multiply with the gravity, and then actually find out the integral value and the second integral value. So basically, this is the denominator of the thrust equation. So look at, if you think about it, this is the denominator of the thrust equation. If you look at the PD errors, the error is the error in theta dot, and integral, state dot integral is nothing but the integral of the rate. So this actually gives you the angle. And last thing is the input, which is the state, error, and then the total. That value goes in here. That actually finds out the input value. So error to input is another function that is implemented later. The last part is you are going to update the integral. So you are going to update the angle. Next thing, you do the same thing for PID, but in PID, you just want to make sure to prevent wind up. You want to make sure that we are not too far from the set point. That is where we are actually implementing this. Total thrust is again state M, state dot G, which is the gravity value, the mass, then the K divided by the cosine of the pitch and cosine of the roll. Then same thing, find the error and find the input, and then update the input state. Then you have to find out error to inputs, which is state, error, and total. And please note that's going to give you E1, E2, E3. These are the three errors in three angles. IX, IY, IZ which are nothing but the inertia properties of the quad, value of K, value of L, value of B, and finally you just have this input. And believe you me, this is the equation for gamma 1, gamma 2, gamma 3, and gamma 4. So gamma 1, gamma 2, gamma 3, and gamma 4. That is where they are calculated. And those will be fed in our simulate equation. And we should be able to see the controlled and uncontrolled behavior. Now, to see, just go to visualize test and just highlight this and evaluate the selection. Again, don't forget to press the button, and then you will see if your controller is working for the appropriate disturbances. So as you can see, you have a little bit of overshoot coming down, coming, and then trying to reach. But finally, it's so please run the simulation. And then you can actually change those PID values and see if it actually stabilizes or basically it destabilizes. That in essence is the PID control of the quadcopter. You are welcome to just run that with PD control. So you just need to supply two inputs. So you can just say PD. And then press the button and see if just PD control is any better. You cannot see the plot, of course. For that, I need to share the screen. But rather than seeing my plot, my suggestion to you is just you run this on your plot. Everyone understood? Any questions? So try this again. And hopefully you would be able to see the code. So I'm gonna give you guys a few minutes to run the code and see if you are getting some good, decent results. And play with the PIDs and then see if you are able to stabilize your pod. Any questions, concerns, ideas, doubts? Any comments? Are you able to run the simulation? I'm looking at the chat window. Are you able to run simulation or no? With control? Okay, so that is the very, very basic PID. Now let's look at the assumptions or simplifications. Our quad model was super duper simple. We actually made a lot of assumptions and we actually wrote 12 simple equations and looked at the quad. Now, in this particular case, we used someone else's code, but I would strongly recommend, and this is just a recommendation, there is no homework or there is no quiz or there is no project on this. Please try to implement your code. So the basic 12 equations, take those 12 equations and try to simulate, try to run those inside Matlab, and then try to write your own code for the PID control. This exercise will give you a lot more insight into how the actual PID works when you are going to, when you go in industry or when you actually implement PID on the physical hardware. So a strong recommendation, take those 12 equations and then from those 12 equations, implement the controller algorithm, and then for the labs, each student will submit. Does that mean we can work? Yes, you can getting the same code to work and we can generate your own reports. Yes. It means you have to help each other out. Some of those labs are intense, and if you do not have any background, it will take. So you can help each other out, but at the end, submit your own work. Does it make sense? So you can help.
Yes, that makes sense.
Yes. So because some of those labs, they are difficult to do for one person, but I would be honest, if you help each other out, that would be really good. Or you can divide and conquer. So the one person would work on lab 1, second person on lab 2, third person on lab 3, and then at the end you help each other out in finishing those individual labs. But please note, you do not need to you do not need to write the code. The code is provided, and yeah, I understand. If you have any concerns about the grading, don't worry, I will talk to the grader and I will try to get that resolved by next week. So if you have any concerns, question about the grades, you can certainly send me an email. Email is the best because then I can forward it to the grader and then I will be in the loop for any grade related questions. So please send me an email if you have any questions related to grades, related to project, and then I would be happy to help. So if you have any questions on project 2, please send an email to Teja and Surya. Yeah, you can send me an email, Kanji, and then I will forward it to the grader. So just email me and I will take care of it. That way, okay.
So, hello, sir.
Yeah.
I have a doubt regarding the labs. Like, is lab 6 different from lab 1?
Yes.
Like, I think, isn't it already implemented in lab 1?
No, he updated the link. So please take a look at the link again.
No, lab 6, not lab 0 and lab 1. I'm
Okay,
taking over to lab 6, collision avoidance detection.
Yeah, I think it's different.
Okay.
But just take a look at the GitHub code, or if it looks same, just send me an email and I will make sure the appropriate GitHub links are included.
Okay.
And my understanding is you can do those labs at home, but if you need a space to do those labs, you are welcome to use Peralta 109, 105, or 103, or Innovation Hub to do those labs. If you don't feel like doing them, I was not able to get access to the drone studio at Tempe because it needs to have security stuff, and then you have to finish the training and all that. So I don't think it's reasonable. But you can do the labs at home, or you can do those labs in Peralta, or you can do those labs in Innovation Hub. Any other questions? If there are no questions, I'm going to stop here today. And I will see you next week.